Assalamualaikum and good morning again. So today is this is the continuation of the previous example of velocity analysis. So today we'll be doing the acceleration analysis. So for this, we still go back to our previous example, which is involving shearing mechanism. We have the same geometry again, but this time we would like to do the acceleration analysis. So we consider in this case the crank doesn't have any angular acceleration. In this case, the doesn't have angular acceleration. That means it will continuously rotate at a constant angular velocity of 100 rpm. So in that case, it's equal to 10.47 radian per second. So we take note of all the dimension here, and then we just revisit again from the previous example, where we have the crank. We've solved it graphically. So we managed to get the velocity for VCB. Velocity of C relative to B is at 5.4 inch per second. VC, which is a velocity of C going vertically upward, is 7.6 inch per second. So from there we can find the relative angular velocity or the angular velocity of BC, which is equal to 5.4 divided by 4 inch. In this case, equals to 1.35 radian per second. So with all this information that we have, we can now continue to solve for the acceleration analysis. From this information, now we need to start list down all the data they already have. I've done the pre-calculation right now. Okay, so we know that the mechanism is rotating at constant angular velocity. That means the crank is rotating at constant angular velocity. So here alpha 1 is equals to 0. So this is from the previous calculation. Omega 1 10.47 radian per second. Omega 2 we just recently derived from the velocity analysis, which is 1.35 radian per second. VCB equals to 5.4 inch per second. VC equals to 7.6 inch per second. Now for the acceleration, to find the accelerations of C, we have to use this formula, which is AC equals to AB plus ACB. And since AC is basically a pure linear acceleration, it doesn't have any more components in that. So it's actually acting only on one direction. So AC is just AC. But AB we have to break up into ABN, normal component, and ABT, which is the tangential component. Same with ACB, we have to break into normal and tangential component. However, since alpha 1 is 0, therefore ABT is equals to 0. And for ABN is equals to omega 1 square RAB times RAB, 10.47 square times 0.75, which equals to 82.2 inch per second square. And now ACBN equals to omega 2 square RBC equals to 1.35 square times 4, which is equal to 7.29 inch per second square. Now there are two components that we need to find, which is AC and ACBT. So with that, we need to start drawing on the line here. But before that, we need to recognize that here is the direction of acceleration, which is ABN, which is at 40 degrees to horizontal, and this is ACBN, which is at 73 degrees to horizontal. So with that, we can and of course AC is vertical. Then from there we can start to plot the graphical solution. Okay, let's get started. First off, we need to decide on the scaling, because obviously this might not be enough to draw if according to the scale. So let's check first, which is in this case ABN equals to 82.2 inch per second square and ACBN is 7.29 inch per second square. I've decided to use a scaling of 1 cm to 4 inch per second square. That means if this one, we just divide by 4. So let's start. I think first off we just since this is 82.2 inch per second square to the right and AC is actually vertical, then we should basically start from the left, so we have enough space to plot. Okay, so 20 something like that. Okay, let's just plot AC in this straight line. Okay, then just draw a 40 degrees line, 40 degrees, this is 40 degrees. Okay, this is the point actually. Okay, 40 degrees. Let's just draw a set line first. Then we measure. In this case, 82.2 divided by 4 is equals to 20.55, which is 20.55 cm. Right. So we have to measure 20.55, 20.5, somewhere here. So oops, 24.55 is here. Now next is ACBN, which is 7.29 divided by 4, which is equals to 1.8 centimeter at 73 degrees to horizontal. So starting from here, we need to measure 73 degrees. Okay. Since we don't have enough space on the top there, we can measure from here. It's also no problem. Just in this case, 71, 2, 3. Okay. 73, and then is 1.8. So if we measure something like this, the point, so it will be from here, and then we go 1.8. Okay. So this is ABN and this is ACBN. Now the direction of ACBT is in this direction at 70 degrees. So we don't know yet which direction, but it's obvious that from here, that for it to complete this part, it should be traveling to the left. Okay, so that means we need to measure 17 degrees from here and then plot it some that way. So 17 degrees. Okay, 17 degrees from the horizontal. Maybe somewhere 7, 10, 15, 16, 17. 17 degrees. Then we draw from this line. Alright. So basically this is ACBT and this is AC. So by measuring, we just measure this. This should be 10. Oh, so 10, that means AC is equals to 10 cm times 4, which is the scale here. So it's equals to 40 inch per second square. For ACBT is equals to oops, it's a bit difficult to measure because of the spacing that I'm facing. So the spacing of the mounting here, never mind. Let's just start from 10. And 10, 16, 26, you can see here is 16. That means 16 times 4 is equals to 54 inch per second square. Let's confirm again. 16 times 4, yeah, 64. Sorry, 64 inch per second square. That's it. We got the acceleration value for AC and ACBT. So we will continue again with the next example.